Hello guys, so welcome back to our course. This is lecture 12 and we're gonna continue our diode applications. We explored enough the diode clipping circuits and now it's time to explore another very important applications which is diode rectifiers or rectifier circuits. So the main objective of these circuits is to convert EC signals into DC signals. Is to convert the signals that is, variable in value and the variable in direction as well, okay, to DC signals, which is constant in value and constant in direction. So let's explore, explain both. What's meant by variable in value and variable in direction. So variable in value, this is, very, clear here. Look at this V input, for example. This is sine wave, okay? And, with the time, it's changing in value. Here it's 0, then, V maximum, then 0 again, and so on. And why I'm giving here the example of a sine wave, because this is what we can generate from nature. If you have, for example, a dam, a hydraulic pressure of the water can, turn a turbine, then this turbine will generate electricity for you. If you have, for example, a gas turbine, this is also another source. And all these sources, they generate sine waves. So we can generate sine waves in nature, with very high power. For example, the outlet, the electricity outlet you have here in your home, it's 110 RMS, which is 110 times square root of 2. It's around maybe 160 volt or 155 volt or something, which is really big. Okay? But there are many applications like your diode charger. It needs a constant voltage. Okay? So we need to convert such a stable, source that we have all the time and we can generate easily from nature into DC signals. And one of the important applications that we can use diode in is such kind of circuits. Okay? So here is a very simple application of such a circuit, which is what we call half wave rectifier. And from its name, we're gonna see it's rectifying just one half. Okay? So we said that the AC variable in value with time here. As the time goes, the input is changing in value, and it's also variable in direction. And let's explain what that means. So in the positive half cycle, okay, this is, for example, V input in the positive half cycle. And in the positive half cycle, for example, when V input is equal to V max, that means that this point, let's call it A, is greater than this point, which we call B, for example, by V maximum. Good. Now for the negative half cycle, for example, at minus V max. At minus V max, we say still, since we put all the time positive here and negative here, we say that A still greater than B, but by minus 10 volt. Which is the opposite, basically. So we can make the direction like this, negative at A and positive at B, and then we can say at the time, that B is greater than A by 10. Okay, but as you see, guys, here, if we go with the fact, this is actually the fact. The fact is in the positive half cycle, in the first half cycle, let's forget about the positive and negative. In the first half cycle, A is greater than B in voltage, and in the second half cycle, B is greater than A in voltage. If we put all the time positive at A and negative at B, then we should draw the sine wave like this. Okay, positive in the negative in the first half cycle and negative in the second half cycle. Also, you can draw this sine wave in such a way that it will be positive all the time. But at that time, we should change, which is a fact, by the way. This is actually the fact. Okay, this is what we see here, positive and negative, just a model. Okay, so you can go back to the fact in which the direction in the positive of the first half cycle is in that way, positive at B, I'm sorry, negative at B, positive at A. And in the second half cycle, the direction it changes and become negative at A and positive at B. Because in the second half cycle, B is greater than A in voltage. Okay. So as we see here, this AC signal is changing in polarity. It's changing in direction. Okay. So we can say that in the first half cycle, the current is pushing in that way. Okay, if there is a current. And in the second half cycle, the current will be pushed in that way if there is a current. This is another way to interpret that. Okay, good. So let's solve this circuit. I mean by solve, finding the output, which is basically now VR. Remember, in all the clipping circuit, we were interested in the voltage across the diode and its battery, you know, if there is a battery. Now we removed the battery and make it zero, or make it zero, let's say that. And we're now interested in VR, which we have done before, by the way, you know. Just take any clipping circuit and put VB there, the voltage of the battery that we usually put in series with the diode, with zero. Then you will get this circuit. Okay. So let's solve it. Let's solve this circuit here and see what we're gonna do, what we're gonna get, and how this circuit can really convert somehow the input AC to a voltage DC, or you know, DC source, or yeah, somehow DC. So let's see. So let's start by the positive half cycle. So number one, we have here two half cycles. Let's start by the first half cycle, which is the positive one. So the positive half cycle. In the positive half cycle, okay, the voltage of A, this point, will be bigger than or greater than the voltage of B. So we can consider the circuit like this. This battery is changing, but it's all the time positive. And this E here, basically, all these values, it's changing with time. And here is VO, which is VR, and here is VD. Good. We know this circuit very well. We know that this circuit, since the E with the diode is connected in forward, so D is forward biased. Then we need just E to be 0.7 so that this diode can turn on. Because if E is, for example, 0.1, this is not enough. 0.2, not enough. 0.6, not enough. 0.7 at that point, which is the input minimum as usual. This is what we call it in the clipping circuits. If you go back to our previous lectures, the input minimum, which is 0.7, at that point, VD will become 0.7. Still, the current is zero. But then, when the input exceeds this 0.7, become, for example, 0.8, 0.9, and so on, then the diode will stick to 0.7, and the rest of the voltage will go to the output, or in that case here, VR. Okay, so when V input or E is greater than 0.7, so in the positive half cycle, we have two regions as well. When V input or E is greater than 0.7, greater than or equal, because this, you know, equal is a transition point, then the diode will be on, and VD will be equal to 0.7, constant all the time. Let's make Kirchhoff here. So VO plus VD equal to E or V input. So VO, which is VR, is equal to Vn minus VD, which is 0.7. The second case in the positive half cycle is when V input or E, call it whatever, is less than 0.7. At that time, the diode will be off. So the current will be zero, the current that flows in the diode. will be 0. And remember, VO is actually VR, which is IR. Since I is 0, then IR is 0, so V output is 0. Now let's make Kirchhoff again. We have the same equation. VO plus VD equal to Vn. So VO equal to Vn. Let's apply this, then go to the second half cycle, or the negative half cycle. Okay. Good. So let's do the diode in red, for example. So let's now search for these two regions in the first cycle or the positive half cycle, when V input is less than 0.7 and V input is greater than V.7. So look here. This is, for example, the 0.7, this point. I just marked it before the lecture so that we don't take time, marking point and stuff. So all these values, as we see here, is less than 0.7. And all these values again is less than 0.7. Okay. So that region here, let's call it 1 or 2, because this was number 2 here in our analysis. So in 2, V input is less than 0.7, so the diode is off. And let's draw this. So when V input is less than 0.7, what we have? We have very simple thing. We have VO is equal to 0, so we just mark 0 here and 0 here. These are the two regions. So this one and this one. Okay. And now let's plot VO. VD. This is VD, guys, not VO. This is VD. So VD is equal to V input. So just copy and paste that portion of the sine wave. And again, this is just a copy and paste. So this red here, this red curve is just copied and pasted here. And again for the other one. Okay. Now let's draw region 1. Region 1, or the first case, which is that one, when V input is greater than 0.7. So all these, so let's do it whatever, with blue, that's fine, or green. So all these values here are greater than 0.7. So what's going to happen in that case? VD is equal to 0.7 constant. Remember, this was back these 2 points here. The tips, the top points for the region in which V input is less than 0.7 was 0.7. As we see here, look. So basically, this is VD. It will be constant like this. And by the way, this is clipping, okay? But since VB, if we go back to the clipping circuits, when we put a battery VB, the clipping happens at VB plus 0.7. VB now is 0. So I just assume that there is, a battery like this, and this battery has a 0 voltage. So the clipping happens at 0 plus 0.7, which is 0.7. Okay? So that's why I'm always, do the clipping first before, although this is more important than the clipping. Okay? Now, that's good. Now let's do VR, which is, by the way, here, our main target. Because this resistance here is actually a load that we want to feed with DC signal. So the target here is to feed some load, like, for example, your phone, with DC signal, which is represented by our load here. So in region 1 here, VO, which is VR, is equal to V input minus 0.7. So whatever the values of V input here, just subtract 0.7. Remember, this is the level of the 0.7. Okay, so that's what you're gonna do. You just take this green dome here, this one that I'm highlighting right now, and just shift it down by 0.7, or take this dome and just put it here. Okay, so the last point here is Vmax minus 0.7. Remember, we take this was Vmax, but we subtract 0.7. This is 0.7. So it will be Vmax minus 0.7. And remember, this is 0.7. 0.7 minus 0.7 will give you 0. And this is also 0.7. 0.7 minus 0.7 equal to 0, because VO is equal to V input minus 0.7. So any point we will subtract from it 0.7. Okay, so this is basically, you know, VO now. Now let's do the negative half cycle, or the second. You know, I really like to name it the second half cycle. Okay, because it may be a negative if we assume that all the time A is positive and B is negative, or it may be just the second half cycle if we, you know, consider flipping which is really, you know, valid and legitimate. Okay, if we flip the directions each half cycle. Okay, so I'm gonna do the second one. I'm gonna flip the direction. Okay, so I'm gonna put the positive here and the negative at A. So I'm gonna flip the direction. If you flip the direction, you must flip also this sine wave here. So you must redraw it. So let's redraw the sine wave. So I'm gonna redraw it with red. Okay, so I'm gonna do that now. I'm gonna make A negative, B positive. And if you do that, then you must flip the values of the sine wave. They must be positive. Then you deal with that positive input that time. So this one here, this is V input, but this is V input now. But this is a negative, this is a positive. This is A, this is B. The first one here, let's draw it with red again. This is V input. This is A, this is B, but this is positive, this is negative. So the direction here was like this, the direction here is flipped. And I'm gonna call it V input dash, you know? This is V input dash now. It's the same as V input that has all the time, you know, direction positive A and negative B. Okay, good. So let's make our analysis with V input dash this time. So second region, let's do it with our normal color. So number 2, a second half cycle. Okay, second half cycle. I flip V input direction and become positive input called V input dash. Okay, good. So this is now the circuit. And look, this is V input or E, whatever. This is our diode. And here is R, here is VO, and here is VD. Here is V input dash this time. I'm putting V input dash. Okay, good. Now let's, now you have a battery, positive battery, like something like this. Example, on a side here, something like this. 5, and this is a diode, and this is a resistance, you know. And now, in that case, is a diode forward or reverse? For sure, it's reverse. So here the diode is all the time. The diode is all the time reverse. So diode is all the time off. So I is all the time 0. So VR, which is VO, is equal to IR equal to 0 all the time. So VO here is equal to 0 all the time. Now let's make Kirchhoff. So let's take this loop here. So VO plus VD, this is VD, plus V input dash equal to 0. So VO and I'm sorry, and the VO is VR is equal to 0. So VD basically equal to V input dash minus V input dash. I'm sorry, minus V input dash. Minus V input dash. Very simple. So VO is 0. Let's locate, let's do that. So let's have again the green. 0 all the time. So this is a negative half cycle from here to here. 0 all the time for VO, which is a very good thing, as we will see later now, maybe in 1 minute or something. And the VD is minus V input dash. Remember, we are dealing with V input dash, not V input, which is the red one here. Okay. If you want to use V input, that's fine. Okay. You will have the same, you know, you will have a battery which is connected forward, but it has negative values. So it's again reverse, and the diode is off. Okay. So basically now, VD is minus V input dash. This is V input dash. So what you're gonna do? You're gonna do copy, but when you paste it flipped. Okay. Or take any value here and just multiply it by minus. So here is 0. Minus 0 will give you 0. Here is, for example, you know what? Here is 0.7. This will be minus 0.7. Here is, for example, V maximum. This will be minus V maximum, and so on. So basically, take this and flip it here. Okay, that's basically, you know, VD, and here is V minus V max. Because when V input dash here is V max, minus V max will be minus V max, like this. Okay. If you just consider the original input in the second half cycle, which will be the negative half cycle, you will find that this equation equal to VD is equal to just V input, equal to V input. Whatever the V input is, just copy and paste. Whatever you want, you know, go with it. That's fine. Okay. Good. Just like what we did with the clipping circuits. We solve this type of, or we do performance analysis using 2 ways. Whatever you choose, do with. Both are correct. And now let's have a moment here, you know, take a breath and look at our output. Remember, we wanted to feed this load with a DC signal, right? And now let's look at this. You may say it's still changing, right? It's still variable with time. We know that DC usually constant with time, but this is changing with time. Okay, so yes, you're right. But how about the direction? Okay, so in the first half cycle from here to here, we have positive values. So this point has a greater voltage than this point, because, you know, this is a positive, this is a negative. Okay, so in here, the direction is that one. But now look at the second half cycle. Is it changing? No, we don't have minus sign. We don't have minus values. So basically here, we could unify the direction. You either have, you all the time have current flowing in that way, from positive to negative. That's why the direction of VO is always from negative to positive. So you either have a current in that way, or voltage from negative to positive, from the ground to the positive terminal of R, or you don't have. Okay, so at least you unified the direction. So this is a good step. This is 50%, because we have two characteristics. The first one is changing in value. Still, yes, it's still our output here. It's changing with value. But the second characteristic for the AC is that it's changing in polarity. So as we see here, the polarity is positive, negative. Here the polarity is negative, positive. But here's this guy, no. This guy all the time positive, all the time in that direction. Negative here and positive here. Okay. So that's basically, you know, our first step, you know, toward, you know, a better and better and better, you know, rectifier circuit. That's very simple circuit here, which we call half-wave rectifier. And now why we call it half-wave rectifier? Because basically it deals with a half wave. Okay, you want to unify the voltage, rectify the voltage, unify the voltage, a voltage that has a signal that has only one direction. Okay, just pass one of the cycles and exclude the second one. That's what happened. We take only the first. So our diode here, okay, passes only the first half cycle, which is the positive half cycle, and, you know, discard, we can say in, you know, informal terms, the negative half cycle. That's why it's called half wave rectifier. It deals with half of the wave and discards the other one. That's why we have a unified direction for some voltage. Okay, guys. So one last observation here is that usually these circuits deals with very high inputs. Okay, for example, and this, by the way, a very practical example and everywhere. Your outlet at your home is 110 RMS. 110 RMS is around 155 or something. Yeah, 155 volt maximum. Very big. And 155 is much greater than 0.7, right? At that time, okay, since 0.7 is really, really very small and far away from the 155, we can neglect this voltage drop here across the diode. And here, one of the applications of the ideal voltage model. Remember, guys, I said to you that ideal voltage model is one of its application when you use it, you know, while you are very comfortable that the result will still be accurate, is when you deal with very high inputs in rectifying circuits. That's now the time for it. Okay, so in the next video, I'm gonna solve the same example here, but using the ideal diode model. Okay, this is till this moment we are dealing with constant voltage model, and this solution is using constant voltage model. In the next video, we're gonna solve the same circuit and explore the outputs VO and VR or VD. I'm sorry. Using the ideal voltage model. Okay, guys, thank you very much for watching this, and see you in the next video. Bye-bye.